Okay, so our speaker today is Nikola Andrejic, and he will tell us about estimating the Jacobian matrix of an unknown multivariate function from sample values by means of a neural network. Go ahead, Nikola.
Thank you, Vitaly. Okay, so the title of this paper is very informative of the contents of this paper. We know exactly what it's about. Okay, so first I'm going to present like the general problem of estimating Jacobians of unknown functions. Then I'm going to briefly mention some related problems to that. Then I'm going to go through the solutions that the authors of this paper propose. And I will provide with one of the numerical examples that they do many numerical examples, but they visualize only one of them. So I'm going to present that one. And then they prove the convergence of their algorithm under certain assumptions. So if we have time, I will go through those assumptions briefly also. So what is the general problem? We have an unknown function f that in general can be multivariate and also have an output of dimension d. So essentially it takes di real inputs and produces do real outputs. And we can refer to this function as a black box. And besides that, we have access to a finite cloud of samples, that is a set of pairs x and f of x. And that's the only access to f that we have. And we need to estimate the Jacobian of f. So what is a Jacobian? Well, that's essentially a second order tensor whose components are first partial derivatives of coordinate functions f with respect to the inputs, with respect to all of the inputs. So essentially it's a matrix composed of these entries, the fi over the xj. What does it tell us? Well, knowing f at point x, Jacobian at x gives us a linear approximation of f at a nearby point x plus h, which is a general idea of a derivative. We can express this through this limit, but using the small o notation, that's more clear. Like that tells us that f at x plus h is approximated by f of x plus the Jacobian times h, where this is the matrix multiplication with the column vector h, and plus a small o, i.e. an infinitesimal of h to the first degree as h goes to 0.
So shouldn't be h squared?
No, this is a small o, not big O. So this tells us a function that is infinitesimally smaller than the function in the brackets, or big O of h squared. Yeah, it's equivalent. Okay, so the simplest proposal would be to train a network N to approximate f itself and then differentiate the network N. But there are two problems. First, a smaller problem is the activation functions might not be differentiable like ReLU, but that's easily solvable because it's almost everywhere differentiable. Then the bigger problem is differentiating a good approximator to a function. In general, doesn't give a good approximation to its derivative, i.e. it might not give any approximation. We'll see what I mean by that. And formally, that's because uniform convergence of a sequence of networks NT, where this T, we can think of this T as snapshots of a same network at different training time. So a uniform convergence of not just ordinary, but uniform convergence of a sequence of networks or any approximators to f doesn't imply convergence of their derivatives with respect to inputs. And authors in the paper provide with this figure. This is an extreme example of that. We can take a sequence of sines with increasing frequency but decreasing amplitude, and they uniformly converge to 0, like to a constant function of 0. But their derivative blows up at every point. which means that we don't even have a pointwise convergence of derivatives. Like they become worse and worse as the sequence goes closer and closer to the function itself. But obviously this translates to approximating any functions with these high frequency modes. And also this translates to overfitting. If the network is overfitted, i.e. it interpolates the noise, no matter how small the noise is, that would essentially make approximations of derivatives completely impossible from the network. Okay, so the authors also cite one of the papers that tries to employ this ordinary naive approach of approximating Jacobians from approximating the functions themselves, and they in that study conclude that this task fails, and basically that the networks may be not suitable to handle derivative signal analysis. Okay, so the problem of estimating Jacobian means we need to estimate partial derivatives. This is from a finite data set, this is a very difficult problem. Why? Because first of all, the data set might not contain, and that would probably be the case, the point with these coordinates as well as the point with these coordinates, where all of the other x's, all of the other real numbers are fixed and only one of them is perturbed. Because then we could like take the difference of the value of the function between these 2 points and find the partial derivative. But because we cannot expect this to be the case, we need to change bases at every point to estimate partial derivatives with respect to this new basis and then rotate the Jacobian back into the original basis. And this is a very computationally costly and can produce numerical errors. But even then, if the functions are noisy, if they have like irreducible noise inside them, then the partial derivatives, well, this term in the estimation of the partial derivative might be large, because depending on the sigma squared of the noise, like if the sigma squared is comparable to delta x squared, then this approximation would break down. But even then, even if we can solve these two problems, we need a regression technique to estimate Jacobians at points not contained in the data set, because this would give us only the estimation at x, e.g. at x1 or at some wait, no, this x1 is a coordinate at some sample point at a particular value of x, but we need to somehow extend this to all values. Okay, so this problem is related to a problem of solving differential equations using neural networks, and authors give some references to papers that do that. But in general, this is related to the problem of gradient estimation, where symbolic differentiation is impossible. For example, if you want gradients for backpropagation, but you cannot symbolically differentiate that, then it would be useful to have a good estimator of Jacobians. Okay, so let's go to the solution that the authors propose. For simplicity, we can start at a function that has one-dimensional input and one-dimensional output, basically a real function, because we can visualize it easily here in XY plane. And let's take some point A and f of A from the data set. And let's also take a nearby point B and f of B from the data set, such that B is in some sense close to A. And we still do not formalize this. And then the authors propose to penalize this value. Basically, if you look at this figure, this is the blue line is a true value of f that is unknown to us, but let's suppose that this is the true value. Jacobian, which is reduced to just a derivative, in this case is the red line, and then the green line is our estimate of Jacobian. And then we want this to be close to this. And yeah, they propose to penalize this, but they divide by the distance between A and B, which I think on this figure, this corresponds to, if you draw this triangle, this corresponds to penalizing tangent square of this angle here, because that would be, yeah, this is f of A plus this, and then this is f of B over B minus A. So that would be penalizing the tangent square of this angle. Okay, so
and in this case, both A and B is in data set, right? That's why you can do it.
yes. So I say that here.
Okay, I see.
Okay, in general, so this is the general algorithm that here I describe in some brief points. So in general, let's take a function with di inputs and do outputs, and the neural network that is supposed to approximate the Jacobian, i.e. it has di inputs, so this is x, right? And it gives the Jacobian in the end. So what they say is, for each point in the data set, we create a list of its k max and r max nearest neighbors. That is, we take x. So k, for this, we only look at the x part, okay? And then we look at all other points from the data set that are within a sphere of radius r max, and then we choose at most k max points out of those points, okay? And that list of points is a list of k max r max nearest neighbors of x.
Random k max points.
Well, if there are more than k max, they do not specify. We can either take random, but I think that you can also rank them like by distance. I think it would be maybe better to rank them by, or they do not specify this, but
I'm not sure whether the close distance is better than further distance, right?
No, I didn't include that analysis, but they have like many numerical experiments given in tables where they like discuss the hyperparameters. So these two are basically the hyperparameters of the model. Then after creating the lists of nearest neighbors for each point, you process the lists as pairs of points, where the first element of the pair is the point itself, and then the second element is its neighbor as defined by this, and then you take all of such pairs. So for x, you take some y1, x, y2, and so on, and then for literally you do for all of those points, you create these pairs, and then you divide them in mini batches. And then you propagate mini batches through the network, and the loss function, the stochastic loss function for every mini batch is basically a multivariate extension of this. So these are all Euclidean norms. This is the estimate of the network, and then this is the loss. You backpropagate and update network's parameters. Okay, and since I wanted to be brief, I didn't want to include the many examples that they have in the paper, but they do provide one visual example where they take a function like this, they sample the points like this, and then this is the true value of the Jacobian, and this is the estimated value of Jacobian. The conclusion is that in all cases, the estimate is very good. Like the estimated Jacobian is a very good approximation to the true Jacobian.
What was the architecture they used for that?
They use the feed-forward network. They like literally say they specify everything. They use the feed-forward network with a few ReLU layers with like 100 neurons and 50 and something like that. So nothing too complicated. And now convergence. So they give proof of convergence of the algorithm under some what they say are reasonable assumptions for f. In my opinion, these assumptions may be in some cases too strong, but yeah, probably they wanted to, like, I think, find a minimum set of assumptions so that they can prove the convergence. And the assumptions are that f is defined on an open and bounded subset of are the inputs, and then f is twice differentiable, such that all of the coordinate Hessians, that is Hessians of the coordinate functions, are bounded above by some L. And then also there is some L prime such that every network satisfies this condition. These are basically Lipschitz conditions for f and J estimate. Then they have some complicated assumption here. They define epsilon such that the data set is epsilon dense, which means that for that epsilon, for each x from the data set, there is y from the data set such that well, there is at least one point within epsilon sphere around x. And then there are some constants r and alpha such that this is satisfied, where u and v are arbitrary nearest neighbors, and then is the number of such neighbors with respect to these hyperparameters. And yeah, and this assumption is to me very problematic, but they need it for the proof of convergence. It basically says that this assumption basically says that the loss must not blow up during training.
Mm-hmm.
So if it doesn't blow up, the conclusion is if 1, 2, 3 through 3 are satisfied and the loss doesn't blow up, then it converges in the norm.
Okay.
Well, I mean, okay, so this is actually, it sounds silly, but I think that, for example, if you take a learning rate of 10 or 100 or something crazy, like the loss will blow up, right? Or, you know, something like that. So it says that you should train your network in a reasonable way such that this is more or less satisfied. And then the algorithm converges in norm, which means that at all x, this is all evaluated at some x.
But so you're saying there are going to be no fluctuations around it? I mean, there got to be fluctuations. I mean, it's not going to converge. Maybe there is this in this epsilon, the answer is hidden. Maybe epsilon will be.
Something can converge and still fluctuate, but I'm not certain about that.
Yeah, it converges, but still because.
No, but then the amplitude of the fluctuations should decay. But I would think that the amplitude of fluctuations around the limit will not go to 0.
Well, I'm not sure how to answer that that question.
I mean, it would be strange if the neural network will really converge and you really go to 0 without any fluctuations. But I don't know.
Maybe the conditions are idealized here. Maybe like most of these are not really satisfied, but they. So
can I ask another question? I mean, I don't know if, so let's say you have a very large neural network and you are want to use backpropagation, but it's so large it takes you a long time to backpropagate. But the reason you want to backpropagate because you want to find the Jacobian, right?
Mm-hmm.
How things change in the output layer with respect to some weights deep inside the neural network. So can you like have an auxiliary network that will help you learn how to backpropagate and whether there will be any limits where that will be useful? Like instead of truly calculating backpropagation, you just train a network that will help you to calculate those derivatives.
So they actually mentioned this in the section of related problems. I didn't include it in my presentation, but there are cases where backpropagation is very costly.
Right.
And so they're already like, but you kind of know the form of the function, so you can do fast Fourier transform or something like that to approximate the Jacobian. So yeah, this might be used as so you have a complicated network to forward propagate, but then to back propagate, maybe it could be used as a surrogate network that would just approximate or maybe approximate Jacobians of the complicated part of the network, like not
That's right.
of the
That's
whole
what I mean.
network.
Like, some weights that are sitting like
So
closer to the input layers. I don't know.
yeah, so
Very
in
closely
forward,
to get there, and then
you take one path, like the exact path for forward propagation, but then you take the approximate path for
right,
back propagation. That seems possible with this.
What
I
was
don't know.
that done like at the level of algorithms ever?
No, they didn't apply this concrete algorithm.
No,
They just
I don't mean them. Anyone like you have a neural network. Back propagation is costly, so forget that. Let's just estimate it, like Jacobian, and then use that. I haven't seen that, so that's why
I personally don't know. Like if anyone knows, but I've seen in the references of this paper, they say that there are such cases, but they still know something about the function through which you want to backpropagate, so they do approximate it somehow, but not by a neural network.
No, you always know the function because forward pass tells you about what the function is. You have lots of forward passes.
Yeah, but you don't use a complete knowledge of the function. Only that. I don't really know the details, but there are cases where you approximate the Jacobian, like you don't use the exact Jacobian.
Yeah. Okay.
And if neural networks are used for that, I'm not sure.
Yeah, that was my question. Can it like have a neural network that will assist the neural network to backpropagate? Thanks, Nikola. Other questions?
Yeah, I've got one.
Go ahead, George.
On slide 13, if you could go over there, are those points the same points at which the fake data was produced? In other words, are these the Jacobians? Like, do those points there and those points there match up? The points on 12 and 13?
That's a good question. I think yes.
And the follow-up question is, did they talk about whether this Jacobian that they've gotten approximated, if it interpolates between the points or extrapolates beyond them at all?
Yeah, they said that it performs well, like it solves the problem of like in the midpoints. It doesn't like give wild fluctuations in between.
And that probably depends on R max, right? Sorry.
Yeah, they also discussed that, like
because if R max is small, it will still.
You don't want to take too large R max, but then you also don't want to take too large K max, like depending there's an intricate interplay between the hyperparameters.
And did they talk about extrapolation beyond the original bounds of
No, and no.
Okay.
And I don't think that would be possible. Like you mean going beyond the actual range of the data set?
Well, it depends on the function, right? So yeah. So maybe this method will not work because it's like too local. But if you are fitting modes rather than then you different frequency modes. So they don't do frequency mode fitting here, of course.
Yeah. Well, if you assume that the function has certain frequency components and then feed mode by mode, then
that's what I'm saying.
Extrapolation would be possible.
Yeah.
But like this, I'm not sure.
They don't do that here. Yeah. It's more local solution.
Cool. Thanks.
Other questions?
Yeah, one from me.
Yeah, go ahead, Stanislav.
I just was thinking, like, can we use these methodics to design networks? So we have this cloud of points, and we emulate like Jacobian we need for back propagation, and we can like estimate what kind of activation functions we can use. So we're not just creating like network with preset activation functions, but this whole cloud of points advise us what kind of activation functions we can use to feed Jacobian we like derive this like cloud of points. So like exactly in the context of like second network, which will advise us to design like primary network.
So you mean to train for Jacobian, which would tell us
Yeah, so we have
what to do to train for F directly.
Yeah, something well, like we have Jacobian, like we know what we wish for backpropagation, and with some kind of like again like Fourier approach, not exactly Fourier, but like something like this, we choose particular like activations. If we collect all of them, it will fit nicely into Jacobian. We just
Are you talking about activation function of the primary network or
yes.
Okay, so you want to say how does the change in the activation function will change the network performance then? Or how does the change in activation functions changes the estimation of Jacobian? Those are two different
Maybe
things.
that's the question of integrating the network, because differentiating usually increases the error, but integrating reduces the error. So yeah, maybe you can train for Jacobian, but then integrate the final network to get to get the original function, and then maybe you have to train it a bit more, because when you integrate, you will get some unknown constants there. So you need to kind of fine tune it to really get F. So I don't know, maybe that's costly, but
yeah, just like this idea just like hit me. Maybe we can use it for designing. Yeah, so we have to, like just Jacobian we integrate, and then we can like decompose in elementary this like result of integration. We can decompose into elementary activation functions, and we get the design of the network instead of just like keeping adding RLUs. We will like design layers, maybe wide layers, not like deep network, but maybe wide and shallow with nicely fitting elementary like activation functions, which will nicely fit and reproduce when they differentiate it. We get exactly that Jacobian we want.
Also the integrated network might be more resistant to overfitting. But that's also very speculative.
Yeah, this is just a like wild speculation.
And they actually mentioned in the paper, they say that, and this is a direct quote, it says, little seems to be known about integration of neural networks. Like they bring up this exact idea of, hey, maybe we can take the integration of it to get the function, and then the next sentence is, little seems to be known about the integration of neural networks. Sounds like something that someone else will be working on at some point.
Yeah, nice area of research.
Sure. Yeah. Other questions? Comments? All right. Thank you, Nikola.